Okay, in this lab session we are going to pick up on transportation problems. They are part of a class of problems called network problems. We ended our last lecture period just looking at these briefly, and we're going to go through an entire example, including how you might organize one of these and build it inside of a spreadsheet. It's one of the kind of problems that I think if we put it in spreadsheet form, it's a little easier to see how everything matches up. You don't have to see automatically how the summation notation works in the sort of algebraic form, which of course you'll be asked to learn, and we'll talk about again. But yeah, so let's walk through it. We have one example. I will show you the GAMS code that solves this, and of course you'll have both examples, and there's a handout that goes with this. I might talk about that just a little bit at the end. But yeah, let's begin our thinking about a transportation problem. So these network models are not described that way for no reason. Really, it's the idea that you have a set of nodes, and then there are these connections between nodes, and really it's about these problems are about, one, describing the sort of paths that exist in the network and the connections that are available. Then that gives you all the possible choices, and then about valuing one choice versus another, coming up with an objective, and solving the problem. And of course what makes them sort of unique is the dimension. The dimension gets, and these are not dynamic problems, right? These are static, one period sort of planning problems, but because you have an option from here, we have something set up as S1, or we could think of it as source 1, and the option to move things to destination 1 or 2 or 3 or 4 or 5, all the way down to whatever the n is on this side. Now you can see I have n used here as well. Maybe a more accurate version would have m versus n, because you could have different numbers of sources and destinations. But that's the style of these problems. Now, good network problems, realistic ones, will have source 1 has 3 options, but it doesn't ship to 4 or 5, or we haven't considered it, those kind of things. So there's some intricacies, but we're going to deal with sort of standard setup. Every source can be thought of as an option going to every destination when we begin these transportation problems. And then we'll keep working through those, and we'll see how we could use the results to make some judgments about the entire network, right? I mean, because if we're really going to do something here, one, it's solve for the best plan, and then, as we've talked about in class, the idea is the starting plan gives you this sort of equilibrium, this plan, or this pattern of shipments in this case, that we have no reason to deviate from unless something happens, right? So the all else constant, we stick with this plan, and we know that all else is never constant, so what we're interested in is sort of, what are the shifts that happen? How do we deviate away from this when something else changes in the economy? So that was something we would call either sensitivity, or if it's a much more explicit description of some issue, then we might call it scenario analysis. Either way, we want to look at the plan, but then look at the sensitivity report that comes out with it, and see if we can make some judgments about what's the sort of value or economic information that exists in this network. Okay, these two tables are from a different book than we've been using in the class. I posted this with the lab, this reading, and let me check. This example is on pages 218 to 223 of the handout the reading assignment that goes with this lab, and it gives you the reading is quite a bit longer, and it includes a lot of different examples only of network problems, and we'll talk about some of them in class, but I wanted to give you the entire scan. But for this example in the lab, those 6 pages, 218 to 223, covered the load. So it's in Chapter 5. It's from Moore and Weatherford and maybe some other authors in the book. But they have this example. I've taught it a long time, so one of the reasons to keep teaching is I know all the answers without having to think about it. But it has what we would think of as a supply side and a demand side. And so here at the harbor, this is a component problem. We've talked about this as well. Transportation would always be some small piece of a larger profit maximizing firm of their agenda. And so we've been given some restricted information and said figure out the best plan given these constraints or given these desirable sort of parameters, right? And so when we get them, we treat them as fixed and we solve for this. And so what we've been told is there are 3 harbor locations that we should think of as the supply of motors. And what this company, the larger company, is in this case study that the chapter works through is a vehicle assembly plant. And so the motors arrive at the harbor, they're from somewhere else, and then they need to be shipped to where the vehicle assembly occurs. And so you have the 4 destinations, the 4 demand sides. Okay, so given the capacity at the different assembly plants, these are the amounts that they need, right? So we have to meet those demands. And then here are the supplies. So this is what arrives at the different harbor points. Okay, so we don't go backwards and we don't say, why are we only getting 500 units at the Amsterdam harbor? And we don't go forward from the assembly line and say, why are we putting together 500 units in Tilburg? Why shouldn't we adjust that? We are confined to how does stuff get moved in between these given these constraints. And if we have a good problem and some good economics coming out of the result around the sensitivity or the scenarios that we might think of around this plan, then we might have some information at the end of this. The goal would be to have some information at the end of this that says, if we were picking among these 3 sources, these 3 supplies down here in Table 5.2, where would we like the expansion to be? Is it true that if we had one more motor in the company, and somewhere to use it, right? I mean, that's one of the issues with this problem is the supply is perfectly equal to the demand, and we'll talk about all of that at the end. But let's say there was one more motor making its way through the entire thing. What source would we like that motor to show up at, and which plant would we like it to end up at, right? And it could be that it is a new motor at Le Havre, shipped to Tilburg, and that's exactly what we do. But it could be we want the new motor at Le Havre, and we're going to ship that to Liège, but then some of the motors that are currently being shipped to Liège get shipped from somewhere else, right? So there could be, you know, the entire story of a network problem is just because you ship one more thing here to here, it doesn't mean that this is the place where the demand went up, right? The demand could go up here, and clearly you're going to have to meet that demand somewhere, but it could cause some kind of cascade of results, right? So that's why we do the analysis and why we try to look for the economic story at the end of these. The setup, so we already have the quantities, and here are the 3 ports, A, B, and C, Amsterdam, Antwerp, and Le Havre. And then the 4 sort of assembly plants spread out through here, and you see the connectors giving us all of these, and it's on a map, so it's giving us an idea of the distance traveled from each of these. And if you look, it has all of the quantity demands over here, and all of the supply maximums over here. So we need to know, how do we compare routes? Well, that's one of the places where we need to find data. We need to know this distance compared to this distance compared to this distance. How do we measure those things? Is it just take the distance? Is it the distance on the map? Right? That's a straight line, and I promise you there is no transport method that takes a straight line between those 2 places. So is it the mileage on a straight line? Is it the mileage someone calculated on the last trip, or is it the average of the last 10 trips? And is the cost per mile the same driving from here to here and from here to here, right? Is there some kind of change that happens after these things? So all of that is the important work in any transportation model. It could be that you have all kinds of sort of intermediate nodes that don't change the decision, the path stays the same, but the cost estimates here versus here versus here could be very different. And it might be important to know those in a more complicated network problem. Yeah, so we're just going to take the cost coefficients as given, right? So the research question in this problem, to my mind, is how do you fill in this matrix? We already have this matrix. So our job is to move forward and deal with the analysis of this data in the network problem given the demands and supplies we've been told. So this problem, the nice thing about them is they appear as data matrices. This cost matrix shows up as origins on the row, defining the rows, destinations or endpoints defining the columns. You end up with every intersection being a cost from shipping from A to 1, from A to 2, from B to 1, B to 3, whatever. So we have all of these different things, and so it would be nice if we could set the entire problem up as sort of a set of linked matrices, and that's exactly what we're going to do. We're going to use a spreadsheet. We're going to build this out as a set of linked matrices and get the full look of it. So So I have my spreadsheet open now, and you can get a feel for what I mean of linking up a set of matrices. Okay. So we have up here that matrix we just looked at. This is the cost. These are the unit cost shipments. So shipping one thing from Amsterdam to Leipzig costs $120. Shipping two costs $240, three $360, etc. And so that's information we're going to use, and we're not going to. That's how we've made the choice to set this problem up. You could think of all kinds of other things. If somebody gave us information on how motors are actually moved, what if they're moved in bundles of 8? Right? You put 8 on a truck, and the cost has some fixed component of moving the vehicle over the miles, and then some weight component. I mean, that's how we might think of a true cost term. We're not doing it that way while we're learning, but we'll get to examples where you can see how that would impact the problem. But almost always at the end of the day, right, it's going to be something about the distance or something about this unit cost, and then you need some activity levels. And so this matrix here, this second matrix, is actually going to be where we set up Excel with a bunch of zeros and say you choose. Okay, you have this unit cost information at the top. You need to assign some choice variables, and we need one for every possible route. Amsterdam to Leipzig needs its own choice variable. Amsterdam to Nancy, to Liège, to Tilburg, they all need their own choice variable. And so we just set up this matrix and let it be all of the choices. And the nice thing about it is we can use the fact that these things are in a row to calculate the constraints. We do not need to do any sum products or anything, because the limit that we're interested in ends up being the sum of the row for Amsterdam. We are interested in making sure that we don't go above 500 shipments promised or planned from this source. And so that means we can just write a summation formula here at the end of this row, sum B9 to E9, and then make it, oops, I don't want that, and then give the right hand side value out here. And so as long as we have all these summation formulas correct, then we're good to go. We have a full set of constraints for the supply or the sources right out here on the right hand side, right on the edge of our matrix. And so it'll be easy to track the choices right up against the constraints. And if it works that way for the sources, then we just have to sort of flip our perspective and use the column to deal with the fact that it's not just sources that have constraints, right? We can't ship more than 500, 700, 800 respectively from the 3 different sources, We have minimum amounts that we need to get to the destinations. If we're going to complete this transport plan the way it's been handed to us and make it work, then we need to get 400 units to Leipzig. Okay, and so when you add up the total number of units shipped from Amsterdam, from Antwerp, and Le Havre that end up in Leipzig, that number needs to be at least 400, and so that's just another summation formula. So we're going to sum down this column, sum down this column, this one, and we'll have our 4 constraints that work on the destinations. Set the right-hand sides up here. And so, you if it bothers you, just that this says left-hand side sign and right-hand side, even though it's vertically oriented, I'm sorry, you can move it. You can move the left-hand side wherever you want. You can put a summation formula over here for the column sums as well, if that helps. But there's nothing wrong with it, just tilt your head to the side or whatever, and it's left versus right. It's really the equation orientation, not the spreadsheet orientation we're talking about anyway when we say left-hand side. Okay, so we got choices up here in a matrix. We have unit cost, sort of the objective equation coefficients, if it's a cost minimization problem, up here. And so what do we need? We need a cost equation. We've got the choices and the constraints dealt with here. We need to get the total cost or the objective equation built. And that is going to make use of the fact that this matrix and this matrix on the interior here, this that I've put a boundary around, we put one around this as well. This matches to this, and in fact, once you multiply this number times this choice, what you have is a cost contribution for the firm for that route. And so you'll see here that what I have is a bunch of formulas, B9 times B3 here. So multiply the choice times the cost per unit, and you get the cost contribution to the total transportation plan of shipments from Amsterdam to Leipzig. Get the same thing here, C9 to C times C3. These are shipments from Amsterdam to Nancy. Okay, so if you add all these up, you get the total cost. And then the nice thing about it is, and you'll see they suggest this in the chapter if you read through it, is you can actually get components of the cost as they relate to the different 3 sources and the different destinations. Now, what to be clear though you have to do is to get to these row sums in the total cost, this total cost by source means that you're summing once to get here. So if you sum over this column, then you have if you sum these 3 numbers up, you have the total cost. If you sum these 3 numbers up, you have the total cost. And so you'll see what I have is one extra cell here that sums the column and then subtracts from it the sum of the row of this row, and then I just say that cell needs to show up as 0. If it doesn't, then I have something wrong in some of my formulas somewhere. So it gives me a way to check that all the cost contributions are being dealt with correctly. What's nice about this setup is, it's compact in some respect, but it's easy to program. It's easy to set up the formulas, because once you write this formula, as long as you've got all the matrices in order correctly, you just copy and paste this one formula to all the cells. You copy and paste this formula across, this formula down, and so you can see it all. And so what we do then is we need to go down here and be sure that we have a summation that works, and this one goes from B18 all the way down to E20, so it's going to add these up individually and give us the objective. If we want to solve it, we just go to solver. You can see I already have it set up. The objective is in B23. It's a minimization problem. The changing cells, B9 through E11. The constraints are over here and there, and just click on solve. So that's the solution you need to get. 121450. You could open answer report, sensitivity report, and we'll have those in the slides. But yeah, here we go. So you'll see that the way this has been set up, it actually finds the row and then the column, and so everything here has kind of a nice setup of from to, from to, from to, from to. So you're getting the source destination listing right here because it's looking for headings at the edge, the first text that exists that matches up to that intersection. Okay, so let's jump back to the PowerPoint and talk through this. I think I've been through most of what's in my slides. So what do we have? We have implementation step 2. This is what we call the activity or the use matrix. So how are we going to, we have all these different options for shipments. These are all, every cell is a route. And so this is the use terms, right? So Excel is allowed to set these to anything it wants, subject to non-negativity. And so it can choose to set this to 1 or this to 10 or this to 20 or whatever. And then we get those constraints built right around the edge. Yes, we've already looked at these as well. So we have all the cost contributions down here, linked up through formulas, and so everything should work well. One of the things that's nice, just while I have it here and I'm thinking about it, is if you were thinking about scenarios at the end of this, how are the scenarios likely to come about? Well, having this model set up this way, ready to give you the total cost of shipments that come out of Amsterdam or the total cost of shipments that come out of Antwerp is nice, because what if we wanted to add a new constraint? What if we wanted to say, I need the minimum total cost while at the same time controlling for the cost at Antwerp, because we expect there to be weather conditions, or that we expect there to be some issue, a union strike. This happens, public workers strike all the time in Europe, that's going on in that municipality, and we want to be sure that in our next planning period we're doing everything we can to avoid shipping from Antwerp. And so we're going to lower this total cost. And we might even say we'll take some penalty above the minimum total cost to be able to get this cost lowered, because we're so worried about that sort of risk that exists. So that's a complicated setup. We'd have to think through it, but we're already set up. We'd have to think about the sort of risk trade-off that we would be willing to deal with there. But we're already set up to do it because we're doing these partial cost, or these cost contributions by source and by destination, right? So we would have that extra summation there already ready to look at. Okay, so we got through the solution. I showed you that, and we looked at the sensitivity report in brief. So let's think about what the sensitivity information is actually telling us. So in the top part here, not sure why this is so. Okay, sorry, I thought the recorder was messing up there. So in the top part up here, we have the activities, right? The adjustable cells of the choices sensitivity. And so what do you get? Well, you get a set of solution values. So the shipments are Amsterdam to Liège is 200, Amsterdam to Tilburg is 300. So the 500 units that we had available in Amsterdam go to those two places. So they're split out. That's interesting, good to know, and it's something that we're going to read through the entire plan, but we're also interested in coming up with some comparisons or some thoughts about why these units get used, right? Why these shipments get made. One of the things we might have done before we did anything else was just a check on our cost matrix all the way back at the beginning. And actually, I'm going to bring my spreadsheet up to. So yeah, let me just reiterate on this. So one of the things we might have done, we've been talking a little bit in class about, can we look at the cost information that we have and make some kind of comparisons or some judgments, some predictions just based off of that. And so one of the things we might do would be sort of a row by row comparison and a column by column comparison. And so we might pick first Amsterdam and say, if I'm going to ship something from Amsterdam, what is the lowest cost place that we could ship that? Okay, and so for that case, we would just be comparing every column, and we might say something, we might pick Liège, right, because it is the lowest cost in this row. And then we could just continue with that kind of analysis and say, give me the lowest cost item in this row. and give me the lowest cost item in this last row. Okay, so we would have three things there in italics, and those would be the solution to some reduced problem that says you have one unit to ship, it is in Amsterdam right now, and it needs to go to the lowest cost destination. That's not our problem, but that's one choice that exists as a sub-problem in our problem. On the other side, you would look at the columns and say, give me the lowest cost. I need one unit in Leipzig. If I only need one and I have every option, then where do I want it from? Well, I want it from Antwerp. And so we might make those underline. And so you look at Nancy the same way and make the lowest one underline, and look at Liège, make it underline, and look at Tilburg, and that's the lowest one in that column. And so what you end up with here is, because we have 3 rows and 3 columns, and 4 columns, the most we could get is 3 intersections where the lowest in the row is also the lowest in some column, and they're spread out, right? They don't share the same row, they don't share the same column. And so here we have a pretty firm prediction that we can make. This is not a direct substitute with this. It's not a direct substitute with this, right? Because they live in different columns and different rows. And they end up being the best choice for this row, best choice for this column, best choice for this column, best choice for this row. So we expect some of the fill in our solution to be from those two things. And if we look down here and see the optimal solution, sure enough, this one gets used at 700 units. It maxes out the fill here. This one gets used. It does appear in our solution. It doesn't max out the fill, but it's a big piece of it. This one gets used, right? So all 3 of these we might have predicted from the beginning. We can't make a lot of predictions without going into a bunch of calculations that say what's the opportunity cost of choosing this versus something else. But we can make a pretty good case that there's no opportunity cost advantage from not shipping from Antwerp to Nancy, Amsterdam to Liège, and Tilburg. And so everything else that's in the problem that causes these not to be used as fill, right, at the level that would fill everything, must be because we need to ship things there because the cost goes up too much everywhere else. Okay, so if we look at that as a way of thinking about this, yeah, that's something that we could check into this. So I don't know of much else that we would do significantly later in the semester. We'll look at sort of matrix comparisons, looking for dominance and looking for opportunity cost or regret numbers that we might fill in when we do some things that are on competition and a little bit on games that could be solved with linear programming. But for now, I suppose it's adequate to just note that this is a fairly low 40 versus 90 compared to 42 versus 59.5. Those are what we would call sort of the opportunity cost of shipments coming into Tilburg from Amsterdam versus Le Havre, from Le Havre versus Antwerp. Yeah, and so that's how we might interpret those things. Yeah, so let me get back into PowerPoint here. Take us back to where we were on the sensitivity information, and we want to point out, yeah, so where do we see that stuff, that sort of next best information? Well, let's pick one that is in the solution, so something like Le Havre to Tilburg, 200 with an objective coefficient of 42. If you look at the objective, the allowable increase, the objective penalties. So this reduced cost column has exactly the wrong name. That's why I don't like this name. I call it the objective penalty because it's increasing to cost. So it's the opposite direction, or it's the reduced sort of preference of the objective equation. And so you end up with all of these. We expect these are like the shadow prices on non-negativity constraints, so we expect them to be positive, because if for some reason you start swapping units that were being shipped to Liège optimally with a 0 penalty and shipping from Amsterdam to Nancy, then there has to be some opportunity cost that you incur, and that is 22.5. If you ship instead of Antwerp to Nancy in full, you start shipping from Antwerp to Leipzig, it's 8.5. And you can see that a direct comparison of the objective coefficient here from 40 to 61 would be 21, but the reduced cost is less than that. That's why I wanted to point out these comparisons, so we can do that first round of comparisons. But it's difficult to make what the true opportunity cost is, because you could reshuffle the entire deck. Once you decide that you are going to pull out and stop shipping the full amount from Antwerp to Nancy and come up with some different plan, well, you have 3 other options for getting things to Nancy. And so it can very well be the case that the direct comparison is not, let's take everything that we were shipping from Antwerp to Nancy and start shipping to Leipzig, even though that's a fairly low penalty cost. Something else could be filling in, and that's why you get something here that isn't a direct measure of what's 40 subtracted from 61. So working through those and finding where the reduced costs add out, sort of net out, can be interesting and something that's kind of useful. There's one other value here that shows up as kind of interesting, and it's a final value, Amsterdam to Leipzig, a shipment that we could make, but we're not making. But the reduced cost or the penalty associated with it is 0. Okay, and so that's a signal. That's a signal on something that we should pay attention to, and it tells us that potentially, right, there's something about this problem that is causing there to be no penalty if it says there's a way to add 1 here and incur no penalty. Okay, and it could be the case. It's not always the case, but it means you have to check for it. Well, you wouldn't have to check for it, but I mean, it's something we could check for, that there's a second way, a second optimal plan that will have exactly 121,450 as the total cost, but instead of having 0 shipments from Amsterdam to Leipzig, it'll have a positive number of shipments there. And of course, the way to check it would be just to set a constraint. Amsterdam to Leipzig is forced to equal 1, and solve that problem. So let me switch out to my spreadsheet and try that. Okay, so I've done that, or I've set this up to do that. Let me show you how. So I have this one cell, and I'm suspicious from the sensitivity report that it might be part of a second solution that exists. To get that solution, or for that solution to be equally sort of valid as an optimal or lowest cost solution or a lowest cost plan, the objective total cost needs to be 121,450. And to test it, I said you'd have to test it before you can make that claim, we would go to Solver and I add this one constraint. Sorry, it's hard to see, but it says B9, that cell right there, has to be greater than or equal to 1. And then I click on Solve, and you get the new solution. Okay, so it says you have to ship 1 unit from Amsterdam to Leipzig. What happens? You end up with a shift here, a shift here, a shift here. So there's, it's a merry-go-round, or like I said, a cascade of changes that have to occur to keep everything in balance. But the total cost stays the same at 121,450. And so it must be the case that this solution that we just figured out for, that Solver gave us originally, I'm going to cancel that away, I don't want to see it anymore if I come back to the spreadsheet. But it must be the case that it's a problem that doesn't have a unique solution. It has more than one. And if you read through that chapter example, you'll see that gives us some flexibility to try something else. Hold the cost at 1 and try to lower shipments from some other place. Okay, because we know what the lowest cost needs to be, and so we can try to use a second objective. A multiple objective problem, or a problem with 2 optimal solutions, means that you can play with some secondary objective. You want to get the minimum cost or the minimum shipment cost out of Leipzig, out of Le Havre. Maybe you think there's a tax regime going on there, or something going on that causes the cost to be a little more uncertain there. Then you could do that, right? That could be your secondary objective. And you would still get the 121450 as the minimum overall cost. Okay, so we got all that from up here. There's one last. Actually, let me move down to the constraints, and I'll talk through those. Every one of these constraints matches up to either a destination or a source. Okay, so we have 3 source constraints here. They all end up with negative shadow prices, or 0. And so the negative values here have an interpretation of cost reduction. And basically it says, if you have one more motor ready to ship today from Antwerp, this number goes from 700 to 701, then you could reduce the total cost by $68. If you have one more motor ready to ship out of Le Havre, all else equal, you could lower your total cost by $18. If you have one more unit in Amsterdam ready to ship, it's worth nothing to you. You wouldn't ship it. And so that tells you that the last motor, if you think about this problem as sort of a ranked choice problem, okay, give me the best unit, the best first unit to ship. Give me the second, the third, all the way up through 2,000 units, right? I'm gonna take the next best alternative. I've already committed the first 1,999 units to be shipped. The last one is just sitting there, and you don't have any more choices, right? Because it's sitting in Amsterdam. You've used up all the possibilities. And so this is basically saying the last unit to ship to finish out this problem came from Amsterdam. It was your last choice, just like picking sides for dodgeball or whatever, right? So Amsterdam is this last pick on the supply side. You can do the same thing on the demand side. Okay, so if I could get rid of shipments to Tilburg by 1 unit, I could lower them, or if I had to take on one more unit at a place, Tilburg, it would increase the cost by 59.5 if I had to increase it by 1, or if I could lower it by 1, it would save me around $60. 200, if that goes to 201, the cost becomes 41. If this goes to 901, the additional cost is 107, and then this one is saying additional cost is 120. So down here, if you were to rank these, if you had to pick a place for one more unit to be, you would pick Antwerp because it has the best cost reduction of all the sources. The second place would go to Le Havre because it has the second best cost reduction, and then the last place picked for dodgeball is Amsterdam. You get this place that's the last in its choices. And so what's going on here is we're saying you rank these from smallest to largest, and the largest of the sources is 0, right? That's larger in value than -68 and -18, and it's the worst source. The best source is the one with the best cost reduction potential, and that's Antwerp. And you do the same thing up here, right? But you can only compare source to source, and then you can compare destination to destination. So if we were going to rank these, we would say the one with the highest shadow price is 120, and it's the worst. Because we would love to avoid shipping things there, right? If we were forced to ship one more unit there, it would cost us $120. That last unit we shipped there cost us $120. That was the marginal cost. It was the dodgeball. It was the last shipment was Amsterdam. The last source out came in from Amsterdam. The last destination out came from Leipzig. Went to Leipzig. And it's part of a multiple solution, so that's why it shows up with the reduced cost, because we didn't actually use it. But anyway, yeah, that's another hint that you might have multiple solutions, is your worst source and destination don't match up here. But we can rank them just by knowing that our goal is to reduce cost. The fact that we would most like to be rid of Leipzig shipments, right, because they have this high marginal cost, tells us they're the worst, and the idea that Liege has the lowest marginal cost, the lowest fill, right? The last unit only cost us 41, says it's the best. And so we can always rank these from lowest to highest in these cost problems like this, best to worst. One other thing to keep in mind, the sensitivity comes out a little bit funky in these. It's one of the reasons you have to go check. If you end up with a solution like this, you need to actually solve the problem and make sure you don't have a sort of an artifact, reduced cost of 0, because the allowable increases here are all 0 on this side, the allowable decreases are all 0 on this side, and that comes from the problem being perfectly balanced. It comes from the fact that there are 2,000 units here among the destinations and 2,000 units here among the sources. These numbers have to match up, and so there's no scenario analysis or no plus or minus that you can think about in terms of the margin here, because any allowable increase that's 1 right here, if we talk about that or we tried to solve that with 401 here, all else equal, that problem fails as infeasible, because now you're telling me I have to get 2001 motor units at the destinations, but I only have 2,000 to ship. Okay, so in that case, you really need to be talking about these as the last unit you shipped, and for these, you can talk about increasing by 1 because it does have an allowable increase, but also it could be the last unit shipped. Okay, so some scenario analysis. What would we do there? You could say, what if there's a temporary shutdown at Nancy, causes demand to be reduced by 20% during this planning period? That's simple enough. We could go back here and look at Nancy, look at the shadow price, right, and look at the allowable decrease. Okay, so as long as it's within 20%, you could just come up with an estimate of it as 107.5 times 200. Times 20% of 900, which is 180. And so that 180 reduction you could value directly off the sensitivity information. You could do the same thing for all of them, right? You just have to be sure that you're within 10% cut in arrivals for distribution at Antwerp. That one you can't do because for sources, there are no allowable decreases, right? The allowable decrease is 0. So you have to set up a new problem to deal with that allows for the fact that you're going to be missing some destination. Some of the constraints on destinations are not going to be filled. What would you do in a case like that? So if somebody tells you that Antwerp now, instead of 700, is only going to have 630 units ready to ship. Well, typically what's done is you add a fourth location, in this case it'd be a fifth location. A fourth source location, and it's just a dummy, right? And it basically has what is the penalty, is there a cost penalty attached to not completing all the shipments? And what you do is you just make the cost really high of using it, and it just serves to balance out the problem and meet the destination. And so you get the true plan plus the sort of dummy with the penalty cost added onto it that fills that in. I think the chapter talks about that a little bit as well, how you would deal with that in a scenario. If you have an interruption, you have to take out one of the routes that are available. You could just put that in. I think the chapter talks about that as well. And it says, let's say that you're not allowed anymore. There's some interruption that says you can't ship from, I forgot the example already, but it doesn't really matter. You can't ship from Le Havre to Tilburg anymore. There's an interruption on the route that you use, and it's just closed off, right? You just set this number to 10,000 or some large number, or you set a constraint right here, just like we did when we said this has to be greater than or equal to 1. Just set a constraint right here and say that it has to be 0, right? So even though it's in your matrix and it's going to be summed up, you can constrain that and force it to be 0. So you have all this stuff you can do. You can either answer them from sensitivity report, or you can set up a new problem to solve it. And then these are the questions you can answer directly from the sensitivity report. We can always come up with an idea of what is the best source, and that really answers the question of, well, if we were going to expand operation at a port, where would we make an investment? And what would it be worth on a per unit basis? And so to do that, we just look for the lowest sensitivity the lowest shadow price on a source. If we were going to expand capacity in an assembly plant, where would the transportation part of the model tell us to do it? Now, clearly, expansion at a port, expansion in an assembly plant takes into consideration more than just the transport costs, but it could be a component of it, right? Investments are bigger problems. They require knowledge of market conditions at the different demand places. They require knowledge of what the construction cost and financing would look like at different places. So it wouldn't be just the transportation, but from a transportation perspective, we look right here at this and say, okay, you're going to give me some expanded capacity. I want it right here. I want it right here at Antwerp because that's where costs will go down on the transport model the fastest, or I want it right here at Liège because that's where swapping Liège for some other destination makes the most sense for us because it has the lowest marginal cost or the lowest opportunity cost. The last one says, what about the routes? Can we rank the routes? Well, really we can only rank the ones that aren't in the problem. Aren't as part of the solution. And so how would we do that? Well, if you're in the solution, if you have a non-zero in this column, then it must be the case that you have a zero reduced cost over here. So there's nothing we can go on to say route 1 is better than 2 versus 3 as long as they're all in the problem. But once we get to routes that aren't part of the solution, we have a perfect measure. This says if you're forced to use this route, 8.5 is the penalty that you face. Well, 8.5 is better than 22.5, which is better than 98.5. And so you could rank these, and really what we're looking for here is what is the worst route? What is the one we are most interested in avoiding? And it turns out to be this Antwerp to Liège route. And it's, somewhat interesting is that Antwerp to Liège is not the highest objective coefficient in the problem, but it does have the highest penalty. It does face the highest opportunity cost, right? So this number here is 100. This number up here is 130, but the reduced cost, the penalty we face, is not so big. Okay, so we're getting pretty far into this. Those are the sort of basic questions. We'll continue talking about those, but those are going to be the sort of quantitative keys we go to. Best, worst, look at the sensitivity and rank those, and then look for that worst route and try to think about how we might rank all those penalty costs. So we could set this problem up and solve it in GAMS, and you have the GAMS example, and it's everything you want in terms of solution, and it'll have all the marginals you want. It won't have the range analysis. We could add it though. We know how to do that now. I didn't put it in there, but it's a pretty basic setup. So what do we need? We need a set for the sources, a set for the destinations, and that gives us sort of an xij choice variable, xij here. We need a transportation objective, z, and we need to set non-negativity constraints on x's. The equations look like this. So it is, I think in class I may have said this is not a double sum. It's because I guess I just wasn't thinking. But clearly the algebra requires you sum over I and then sum over j, right? So you can't sum over the entire matrix that way, but what you do is you sum the rows first and then take those sums that you've been given at the end and you add those up to get the total cost. So sorry if that misled anyone, if that was confusing. I have different parameters here for the sources versus the destinations. That's not exactly a requirement. You could have a single parameter there setting up the boundaries, and we'll talk about in another sort of exercise looking at GAMS in a little more depth how you might use something called a superset to set up all of your locations. So instead of having 3 cities in one set and 4 in another, you might have one set that is just cities or locations, or we might call it, since it's a network problem, nodes. And then we set up the second set or the subsets as the harbors or the origins, and the other ones as destinations. So that'll be, as we sort of continue to get exposure to GAMS features that might help us, That's one way we'll look at this, but we didn't do it here. We set up a different equation for supply and demand, and we get those here. And we are going to need different equations because of the signs we have, less than or greater than. Solve the transport, and then at the end I'm going to use a display statement to get the results I want at the end. X dot L, X dot M, supply, the margin on the supply equations, the margin on the demand equations. So 3 sets of sensitivity information there, plus the solution. Anyway, that's the algebraic setup. So the cost is a double summation. The supply, right? You have one of those for each source, and so it's summation over the destinations. Demand is one of those for each destination. It's a summation over the origins of the supply or the sources. Okay, so we have some final thoughts here, thinking about this balance in the model. It's something that if you read the 5 or 6 pages I told you there, it's going to talk about it being a balanced transportation model, and that's important as a concept because it gives us, we've talked about these results before, these knife edge results where everything shows up as binding, right? The left-hand side and right-hand side are equal all the time. Well, this one's by design, right? We've set 2,000 and 2,000 as the total. 2,000 things go out, and that's the most that can go out up here, less than or equal to. 2,000 things have to arrive, and that's the minimum amount that can arrive. And so if you have something that has to be simultaneously less than or equal to 2,000, but also greater than or equal to 2,000, there's only one option, and that's 2,000. And so the implication is the total supply equals total demand is always going to hold at a value of 2,000. It gives you that one-way interpretation of shadow prices. So the allowable increases or decreases will be equal to 0. One or the other will be equal to 0 for every constraint. And so technically that shadow price only exists as the last unit in some regard. It's purely marginal, right? Purely marginal to expansion for supply or purely marginal to a reduction for demand, because the only way you can interpret the shadow price is if you move from a situation where total supply is equal exactly to total demand, or whether that changes. So that total supply exceeds total demand. Another thing you get, one of the constraints is going to have a 0 shadow price. It's always going to be the dodgeball case, right? It's going to be the last thing that gets used. And so Amsterdam, that shipment from there, we would love to avoid it. We wouldn't do it if we could help it, but it got filled. It got filled because there was a requirement for total supply equal to total demand. And so that's the second implication discussed here. So that most expensive location is going to be the last component of the solution, and that's going to be there. So any network model where the source side is balanced up to the destination side will have that issue. It'll have that result. And you can think about it like the degrees of freedom issue in statistics, whereby if I know 10 people, or I see 10 people, and you tell me the average height is 5'8", I only need to calculate the first 9 people's, I only need to measure their height, those first 9 people, because the last one has already been given to me. I can back it out of the average. There's no getting around the fact that their height is exactly equal to whatever the remaining component is in the average. So that's why you end up losing that degree of freedom on that last constraint, because the total supply equals total demand takes over at some point towards the end of the problem, and you just end up having to fill out the total demand versus total supply. Last sort of thing here I'm going to talk about just a little bit is transportation problems. We definitely might start thinking about integer issues here. We definitely couldn't say let's ship a half a motor to destination A and a half a motor to destination B. But it turns out, because of the linearity of this problem, when you look at those solutions, as long as the requirement is in integer units and the maximum amounts that can be shipped are in integer units, then the activities are going to show up in integer units. And we'll talk about this a little bit in class, but you could think about it on your own in advance of that. the way this problem works is you have the entire matrix. Let me scroll backward. Yeah, you have the entire matrix here to choose from. And let's say that this is the first, I guess it was this one. Antwerp to Nancy is the first thing that gets chosen, right? If you were just ranking these out and picking it. Okay, you take one unit from Antwerp, ship it to Nancy. Well, if that was best for the first unit, it's going to continue to be best for the second, for the third, for the fourth, until you hit a constraint in the problem. Until you hit either you've shipped everything that can go out of Antwerp, or you've filled up all the demand that's required at Nancy. Okay? And so we saw that. We saw that Antwerp to Nancy got filled at 700, and then the question becomes what to do with these next 200 units out of Antwerp, how to get the next 200 units to Nancy, given that Antwerp is now sort of off the table, right? It's already been picked for dodgeball in full. And so Nancy now shows up with, like everything else, with either Amsterdam or Le Havre, and then the model says, give me the next best thing to start filling this problem out. So the way that works is, if it's linear, if the problem's linear and there's no marginal cost, so no bend in these cost curves that say once you start shipping 10 or 15 units that the cost has a tendency to go up, then you're not going to have any changes, right? So you'll always fill at the integer level that show up in the constraints, and so it doesn't become an issue for the choices. But it could matter, right? We know shipment, we know transportation is not as simple as just moving the item, right? They usually get moved in batches. And so loads of motors may have different cost profiles if it's only half full versus 2/3 full. And so if we were talking about loads and we want to have integer constraints to avoid partial loads on vehicles, we might have a very different profile of the transportation. So that's something that we'll circle our way back to is how could integer value problems where we need to restrict those, when we do integer linear programming, we'll come back to that and deal with that problem. But for now, the kind of problems we're going to do, it's not going to matter. But it's certainly the first really big indicator that integers might matter because the costs may not be able to be parceled out on unit by unit basis. Even if it's the right way to estimate the cost, the true cost accounting may not want to take those in. Okay, so we talked about a lot here. If you look at the handout, there's a reading that you have, and that's from Moore and Weatherford, and it says 218 to 223 are the pages. But there's also a lab handout that we have. It talks through this, a lot of the same things I've given you. So it's looks like it's 3 pages of notes, and then on page 4 and 5 are some practice problems. And so I just wanted to mention that you have those. So you have the example in spreadsheet form and GAMS form here of this model, the Le Havre, Antwerp, Amsterdam problem. I don't know what to call it, the motors problem. But the practice problems give you another example, and it turns out that example problem I give you is from the practice problem that's in that handout is the transportation example that comes bundled with your GAMS software. It's the transportation model in the model library, and so you can play with that one if you want to see another one. We'll be working through those examples in class, and then there's a second problem in in your handout that takes a different look at transportation. It says, what if instead of being shipment of this unit to here, what if you had a person or a machine over here and it needed to be assigned to a task, right? So what if you had 3 trucks and you needed to decide how to, ignore Tilburg for a minute. You had 3 trucks and 3 destinations there. You had to make these transports. What if you had information you could only ship or you could only assign 1 truck to the shipments that go to Leipzig, one truck to the shipments that go to Nancy. How would you do those assignments? And so you're given a problem example there that it's treated and it's solved in the same way. There's lots of little unique differences. So when we finish talking about transport problems in lecture, we'll move on to that kind of problem that's exactly an exact analog of transportation, just with a different sort of concept behind it. It's called assignment problems, right? So the classic one being, how do you assign AGEC 552 plus thousands of other classes to all the buildings and all the time slots at Purdue, right? That's a large assignment problem, large scheduling problem. With that, I think we'll shut down. We're just a little over an hour, so this is a replacement for our class, and so that's about the right time, given when you practice everything. So hope you've followed along well, and you have a good start on your assignment problem on transportation. But we're going to keep working through these and talking more about what information is required to fill these in, and just how much economics can we glean out of our solutions as we try to backtrack through these problems that, in some ways look like picking teams in dodgeball. So with that, I'm going to shut down and start the encode on this.